All right, the Pleasantville Memorial Day Parade is coming down Main Street. It's 840 meters long and it moves at a constant speed of 60 meters per minute. Okay, let me underline this data, important stuff. 840 meters long, 60 meters per minute. And Deputy Dan runs from the front of the parade with a constant speed that is 3 times the speed of the parade. He talks to Deputy Dave at the end of the parade for 1 minute, and then he runs back to the front of the parade at the same speed. Okay, 3 times the speed of the parade. How many minutes does it take Dan to return to the front of the parade? Alright, well, we can work this out with distance equals rate times time. Alright, so let's first of all look at the front to back. Okay, he runs front to back, then he talks for a minute, and then he runs back to front. Okay, so let's break it down into those time intervals. So first of all, he runs from the front to the back. He has to run. Now, how far does he have to run? He has to run, well, it's 840 meters to the front of the parade, but the parade keeps moving forward at a constant rate of 60 meters per minute. And Dan's running at a constant rate. That's 3 times 60 meters per minute, so we could say that's 180 meters per minute. Okay. And but as Dan runs along, the parade is also moving along. And usually when we talk about speeds, we're always measuring it with respect to the ground, right? Because we think of the ground as not moving, but in actuality, the ground is moving, right? The Earth is turning on its axis, and it's going around the sun, so it's not necessarily stationary, right? So we can actually change our frame of reference. We can change our frame of reference to be the parade itself. And we can measure the speed relative to the parade instead of the speed relative to the ground. Okay, so it's almost as if we could almost treat the parade as if it's not moving, but if we do that, then we have to adjust the speeds, right? You've probably noticed sometimes you're riding in the car and you pass another car that's going close to your speed but not quite. And if you just look at yourself and the car next to you as you're going past, I mean, it doesn't really look like they're going very fast if you ignore the rest of the world, right? You know, they might be going 60 miles an hour and you might be going 62 miles an hour, so they only look like they're going 2 miles an hour relative to you. So we can do the same thing with this parade, okay? Let's kind of pretend like it's, Dan and the parade are all there is in the world, and let's measure Dan's speed relative to the parade instead of relative to the ground, okay? And if we do that, we can sort of treat the parade as if it's stationary, okay? So, and we're interested in time, right? So I'm going to change this equation, divide both sides by r, and I get time is equal to distance over rate, okay? So we're going to treat the parade as if it's not moving. So Dan's going to run 840 meters. Oops, 840 meters. Forgot my 0. Okay, he's going to go 840 meters. He's going from the front to the back of the parade. So the parade is going to look like it's going past him faster than if he, because the parade's going this way, and he's running from the front to the back, so Dan's going this way. Alright, so their relative speeds, it's going to look like the parade is going faster than if he was standing still. Okay, so he's going 180 meters per minute with respect to the ground, but relative to the parade, he's actually going 240 meters per minute. Okay, oops, minute. Okay, so that's the 180 Dan's speed relative to the ground, and 60 is the parade speed relative to the ground. So in this case, their speeds are going to add, and So he's gonna, because the parade is moving past him on its own at 60 meters per minute, then it's gonna make it seem like he's going past it faster. Okay, he's going 180 meters per minute. Alright, so let's simplify this. We can cancel the 0. We can divide by 4, right? And it looks like we can divide by 3 as well. So we end up with 7/2, which is equal to 3.5 minutes. Okay, so that's how much time it takes him to go from the front to the back. And then he talks. I'm going to put that time in here. He talks for 1 minute. Okay, and then he goes back to front. Okay, and now, you know, he's moving the same direction as the parade. Okay, so it's going to look like the parade's going slower than it would otherwise. So Dan's speed relative to the ground is 180 meters per minute, but the parade is now going the same speed as him. So so the relative speed with respect to the parade is 180 minus 60 meters per minute. So that gives us 120 meters per minute. Okay, so that's Dan's speed relative to the parade instead of the ground. And the parade is still 840 meters. So let's see now. We can divide both of these by 40, right? And that's 21 and 3. So it looks like it's going to be 21 minutes. Whoops, what am I saying? Not 21 minutes. Where did I get that? Yeah, 21 divided by 3, so that's 7 minutes. Alright, so let's add all that up. So we have 3.5, 1, and 7, so that's 11.5 minutes. Okay, so it's going to take a total of 11.5 minutes for Dan to run from the front to the back and talk, and then run from the back to the front again. Okay, and the key here, you know, the one thing that makes it a lot easier is if you use relative speed and you are essentially changing your frame of reference so that you're not measuring things with relative to the ground, you're measuring things relative to the parade. Okay, so there you go.